Hello, everyone. Welcome on another run of the Flattender Networking broadcast. Today we will talk about the EVPN. We will uncover the principles. We will do the introduction to the EVPN. Who attended the last session would hear about the BGP-based services. You saw some of the first slides, which I will be presenting today. But we will go more to the details. We will try to really go over all the principles of the EVPN. I will let you understand how EVPN and mainly with the MPLS data plane works. So we will see in the next let's say 45 minutes. My name is Jiří Chalupka. I'm a Cisco Technical Marketing Engineer, and let's go for it. So just the objective again, like who didn't attend the first session, the objective is to have a really short technical session without any registration, without any fee. We will talk mainly about the topics from the service provider environment or service provider data center technologies. So really technical. It will not be any marketing. So let's go first for the EVPN part. So here you will see like today really we will go more to the details. So I will not do again the introduction which I was doing the last time. So I'm expecting everyone to see like last presentation. You can go back to the e-vpn.io and you can look at the slides from the previous session. So here like a really basic picture where I'm showing what is the difference between the BGP-LC VPN and EVPN L3 in terms of like the signaling and the data plane. I think it's a very basic. And on the other hand, we have also the BGP L2VPN. When we will bring this the services overlay and we are using the MPLS transport, we can see that in the end of the day, from the transport point of view, it's a completely same. It doesn't matter. Only one thing what is changing is that on the top of the service label, which is here signaled by BGP, we are putting the IP packet in case of the L3 VPN, and we are putting the L2 frame in case of the L2 VPN service. I will just do the very quick reminder here. We showed like why we are talking about the EVPN, and really I will go to the details in the next slides. So I just want you to see here again what we are trying to solve by EVPN. So first here, like the first problem is that when CE will be multi-homed to the PE1 and PE2, and when we will compare it with the VPLS, when we will go to the VPLS and we will look at like what is the VPLS technology limitation. So here the CE is connected to PE1 and PE2. In case when the CE will send the broadcast, unicast and multicast traffic, the PE1 will basically take this broadcast and will flood it in the VPLS core. When the traffic will come to PE2 and PE2 will send it back to the CE1. And basically there is no way how you will solve this problem with the VPLS. So this is something we will talk about how we are doing this in the EVPN. Next picture, the PE1 basically will flood the broadcast over the core. PE3 and PE4 will receive this traffic, and both of them will send it to the access. So you will see the duplicity on the remote side. The next one is that when I'm doing the balancing over the core, so it means that the PE3 will always see the MAC address M1, which is coming from the remote side, from the both the PEs, because VPLS is the full mesh of the pseudowires. So it means that one the MAC address will come over the pseudowire, which is coming from the PE1, and second time it will come from the PE2. It means that PE3 will always override the MAC address table. So let's go more on the details. So first, let's again talk about like the basic concept. You probably saw some of the basic pillars here. The most important is that we have the EVPN instance. Here, the EVPN instance means that in the bridge domain, I have my traditional access circuit, from the access, and then I have my EVI to the core. This is very important because it's basically completely same what I have for what I have for the VPLS. Only one thing, what I'm changing is instead of having the VFI interface, I have my EVI interface for the EVPN. The second part is the Ethernet segment, and about the Ethernet segment we will talk more in the next slides because it's actually very important to understand this one. We need to somehow let know to PE1 and PE2 here on this picture that the Ethernet or the broadcast domain is the same on both of the PEs. So on this example, the CE1 it's not so interesting because it's just the single home CE, so it's very simple. But for the CE2, you are basically multi-homing to two PEs, and the PEs they need to know that basically it's the same broadcast domain. There is no any signaling. There is in the L2 you are not getting any BGP or any other protocol to let you know that same MAC address is basically behind the both of the PEs. Another part is the BGP routes. Again, we are talking about a BGP-based control plane, or we have BGP control plane. So we will be covering the first 4 routes here. These are most important, and we will go over the details in the presentation. Each of the routes has extended community. So this extended community is carrying the additional information. You can go and you can then check for more of the details after the presentation. So last time we were also showing the load balancing mode, right? Here, the most important one again is the all active. The all active one is where you are cheating the CE. So basically, the CE has a bundle to PE1 to PE2, and CE is like expecting that there is single device. So it's completely transparent bundle, and you are doing the balancing per flow. So this is not like a multi-chassis LACP or any other this protocol where you cannot do the per flow load balancing. Here, really, the CE thinks it's connected to the single device. This is the most important use case for the EVPN. And if you will think about EVPN, you should definitely consider this one as the primary load balancing mode for the EVPN. The next one is the single active. The single active is where the CE has 2 completely independent uplinks, and basically initially will send or basically will flood the traffic on the boat, and only one will reply. So basically, we can also do it like per VLAN. So basically, one VLAN will be active to PE1, second VLAN will be active to PE2. But you don't have a transparent bundle configuration on the CE. So this is very important change. Why to use something like this? The people or the customers are using this mode when you need the QoS on the PE. So you want to be sure that the traffic will go over just one PE. The last one is the port active mode, which is also very interesting from the CE point of view, because you have again the transparent bundle. And what is happening here is that you are driving from PE side. You are driving that only one side is active at one time. This is again when you want to achieve just a single active type of the balancing, but at the same time you have a CE with the bundle configuration, and the PE is signaling on the LACP layer which one will be active and which one will be standby. So these are the 3 most important modes, and we will right now go over more details in the all active, because you will then see that basically the single active is kind of like the subsection of the all active mode. So first, the Ethernet segment for the multi-homing, right? So here you can see that I have 4 devices for the access devices which are doing the multi-homing. L1, L2 are multi-homing the compute with some VMs. L3 and 4 is also multi-homing the compute with another VMs. And again, like if you think more about like the PEs and CEs, it's completely same, right? This is just an example in the data center. So when the L1 and L2 are multi-homing the same or same Ethernet segment or same device over the same broadcast domain, basically again they are cheating the compute one on this picture. You need to configure the Ethernet segment value. So basically L1 and L2 will configure this 10 byte global unique Ethernet segment value. Both of them, you as an operator, you are responsible to configure something like this. Completely same will happen on the L3 and L4. So these two are also multi-hoping same Ethernet segment. Now, what will happen with the MAC address learning, right? So initially, the L1, let's say the L1 will receive the MAC address on the port on the Ethernet, to the compute, and will basically advertise this MAC address over the core. So this advertisement is something very similar to what you have with the for example, with the prefixes, what we know from the VPN v4, VPN v6. But here, the L3 and L4, they will learn this MAC address, and they will basically update the MAC address table. They will point to the L1 over the core. But what is very important here that L2 will take this MAC address and will really synchronize the MAC address table. What does it mean is that basically L2 will point this MAC address to the local Ethernet interface. This is very important. Otherwise, L2 would forward this MAC address back to the L1, and then L1 would forward it to the compute. But because L2 knows that they are sharing the same Ethernet segment, and this MAC address came from this Ethernet segment, L2 can point directly to the local interface. So you are really getting like all active load balancing from both of the leaves here. Important thing, initially, what will happen is that you will receive broadcast, anonymous, and multicast traffic. Of course, you have to flood it in the network because it must be completely transparent. For this one, basically what we are doing, for example, on IO6R is that we are doing the ingress replication. So we will basically send this broadcast, anonymous, and multicast traffic over the core. So L2, L3, and L4 will receive this traffic. There are two service labels in each EVPN instance. There is this something what we call like a BAM label for the broadcast, and there is also one label for the unicast, and we will talk about the details in the next slide. So when I will do this broadcast, I will send the broadcast. I will basically flood over the core. So let's say here, like the L3 and L4 will receive this broadcast. Let's first not talk about L2. L3 and L4, both of them will receive this broadcast, anonymous, and multicast traffic. So what is the challenge here? How to basically agree who will send this the broadcast, anonymous, and multicast traffic to the access. Otherwise, normally both of them would send it to the access, and you will see the duplicity on the C2. So basically, there is a DF election happening between the both L3, L4, and L1 and L2, and they will agree per instance, who will be forwarding this BAM traffic to the access. Now the question is, okay, when they will agree, there is an algorithm, how they are basically how they will compute if L1, L2 is or L3 and L4 are the DF for this particular instance, for this particular Ethernet segment, and for this particular EVI. The question is why I need to have the extra BAM label. The reason for this extra BAM label is that for the unicast traffic, for example, you don't want to follow the DF. If the unicast, which is not flooded over the core, will come to L3 on L4, you want both of them to send it to the access. Another reason is that you need to know if it's unicast, because if you know that it's unicast, you can do the fast reroute, you can do the redirect, you can do a lot of stuff. With the BAM traffic, you must be very careful. You cannot send the BAM back to the core. Otherwise, you can create a loop. Now we didn't cover the part where basically L2 also receive this broadcast, anonymous, and multicast traffic, right? So basically L1 will flood it over the core, L2 will receive it, and now L2 would forward it back to the access. Here we cannot use the DF mechanism which we used on the remote nodes, because imagine that here in this case the L2 would be DF for this particular EVPN instance, right? And you are not able to control if the C1 will send this BAM traffic to L1 or L2. So what we are doing here with the MPLS data plane, we are actually imposing one additional label. So you have your transport label to reach the L2. You have your BAM label to transport the multicast for this particular or broadcast, anonymcast, and multicast traffic for this particular EVPN instance. And then you will impose additional label, which will tell to L2, hey, this broadcast is coming from this particular Ethernet segment. Don't send it back to the compute. So you will basically protect the loop, like local one, coming from the access back to core and again to the same access. Question is why I'm sending actually, because when I know that L2 will drop this BAM traffic, why I'm sending this BAM traffic to the L2? The reason is that I have also an additional compute which is connected. I can have this additional compute which is connected to L2, which is in the same broadcast domain, where I have to send this broadcast, anonymcast, and multicast traffic, right? So I need to be sure that it will be transparent. So the VM here in this picture sitting behind C11 has to receive this broadcast traffic. So I want to be sure that this broadcast will be just blocked back to the access coming from the same Ethernet segment. Another very important part of the EVPN is like the convergence, right? Because think that you will have for example in the data center you will have tons of the VMs sitting behind the compute, and imagine that in this case, let's say there is a 10,000 MAC addresses behind L1 and L2, and you will lose the link between L1 and the compute. So what will happen normally, you will have to go and in the BGP control plane, you will have to withdraw all the 10,000 MAC addresses. So BGP control plane has to send 10,000 times, withdraw for this MAC addresses, right? It will take a time. So over this time, the L3 and L4, which will be forwarding to this particular MAC addresses, will be black holed if it will be forwarded over the L1. At the same time, I know that I have my second node L2, so when I will be forwarding only to L2, I will not get any black holing, and the traffic will go through without any trouble. Because of this, we are basically following the forwarding chain because we are advertising this Ethernet segment together with MAC address. So basically, everyone knows that this particular MAC address is behind certain Ethernet segment. So when you look at the formula which you see on the right side, the MAC address is pointing to ESI. For example, ESI1, which is connected to leaf 1 and leaf 2. So when the link from L1 to compute goes down, so it means that this particular Ethernet segment is going down. So L1 will send just one message, basically one withdraw, and will inform the L3 and L4 that basically this Ethernet segment is not available over the leaf 1 anymore. So any MAC address which is pointing to this particular ESI, 10,000, 100,000, and so on, is automatically withdraw from the leaf 1 is pointing just to the leaf 2. So you need just one single BGP withdraw to inform everyone about this topology change. So let's go right now. We covered the most important part. Basically we know how to do the broadcast, how to basically advertise the MAC address. We know the DF election. We know the split horizon label. Let's do the EVPN like a startup sequence on the real example from my lab, and let's see what's happening. How I'm sending the information, which route types I'm using, and so on. So first one is the DF election. The DF election basically it works like that. We are using the route type 4 in the BGP EVPN address family. So basically R36 and 37 say, hey, I have this particular ESI because you as an operator, you are responsible to configure this ESI. So in this case, you can see that here is a route type 4 coming from router 36, and completely same will also happen on the 38 and 39. There is by default, there is a well-known formula how everyone will compute if it's DF for this particular EVI. So basically, if you will have, for example, EVI 100, and you are doing the dual homing, like in this case, you will take the EVI 100 modulo by 2, and you will get a 0. So the router with the lower BGP router ID will be the DF for this particular EVI. When you will have a EVI 101, again, you will do the 101 modulo 2, and you will get the 1, so router 37 will be the DF. And completely same will happen on the router R38 and 39. The next one is a route type 1, which is there per ESI. We will also talk about route type 1, which is there per EVI, but this one per ESI is there basically to advertise the split horizon label, and is there also to work for the mass withdrawal. So with this one, you are also you are advertising the split horizon label, which is used for the local loop between R36 and 37, and also for the 38 and 39. But at the same time, you can also see in the detail of the message that you are also advertising in this route that this particular Ethernet segment is, for example, all active. Yeah, if it will be single active, you will advertise the different flag there to let everyone knows that you are using the different balancing mode. The next one is the basically route type 3 for the BAM. So basically with this one you will advertise which type of the multicast replication you are using. Here in this example you see that it's a type 6, which means ingress replication, and you are advertising the BAM label. So everyone will advertise this BAM label between each other. So let's look at the packet, like how the packet goes over the network. So first, the packet will hit the router 36, for example. So basically, from H1 will go to router 36. Router 36 will basically replicate because it's a BAM traffic. It's a broadcast, for example. So we'll create a packet for 38 with the label from the 38 with the EVI 100 in this example, and there is the original the broadcast frame. Same it will be for router 39. And as we discussed for the router 37, what will happen is that I need to impose the split horizon label, which I received earlier by a route type 1. So basically based on this, router 37, when we will receive this broadcast traffic, will, based on the split horizon label, will block the forwarding from router 37 to host H1. Now, a very important part is also the MAC advertisement. We didn't cover this most important thing. So once I will receive on router 36, again in this example, I will receive the MAC address. I will use the route type 2, and over this route type 2, I will advertise this MAC address over the core. So again, what will happen is that 38, 39 will update the forwarding table, and 37 will synchronize this MAC address in the MAC address table. So basically, it will point to the local interface facing the H1. Again, because you can see in the detail of the BGP update that I'm also sending the ESI. So router 37 knows that it's coming from the same ESI which is locally attached. So router 37 can point directly to the same interface. Then from the forwarding point of view, when the router 39 will receive the flow, which is for example for H1 in this case, the R39 will put the transport label of 36, will put the EVI label or this label for this particular MAC address. What we are doing, we are allocating the label per bridge domain, so it's more scalable solution. So you are not allocating the label for each of the MAC address, and you will send it to router 36, and router 36 will send it back to the access. Now, the important part is how to let know to router 39 and 38 that they can also send these packets to router. They can send another flow to router 37 because 37 is also multi-homing the same internet segment. Actually, 38 and 39 they already know this from the advertisement of the route type 2 because it's coming with the Ethernet segment. and they already know that this Ethernet segment is connected to router 36 and 37 from the route type 1. But what they need to know the label of the EVI 100 on the router 37. So for this part, we are using the route type 1 per EVI, which will basically advertise the label of the EVI 100 from the router 37 in this example. Basically, again, like all of the routers, they say, hey, we are using this label for this particular bridge domain. So if you will see that some MAC address is coming, from the Ethernet segment which is connected to me, and I'm using this particular EVI instance, you can also forward to me, so you can do the balancing. If we will look at like what's basically happening from the EVPN point of view, this is something what we call aliasing. You can imagine this as a BGP multipath in, for example, VPN v4, VPN v6 example. So then when I'm sending the traffic again, like from the H2, so one flow is going to router 36 as we described. But when I will have another flow where there will be, for example, another source MAC address, I can hash the traffic to the router 37. So you will see that I'm basically getting really per flow load balancing over router 36 and 37. So this is EVPN aliasing, and again, it's very similar to BGP multipath in L2VPN world. Another important part of the EVPN, like the L2, is MAC address mobility. In the data center, in the same subnet, you can move the VM from the compute 1 to the compute 2. What will happen here is that initially, in this example, the VM MAC address was learned over the L1. When you will move the VM, let's say behind the leaf 3, once the VM will send the first frame and leaf 3 will learn this MAC address, the leaf 3 will basically advertise this MAC address over the route type 2, as we learn, with the higher sequence number. So basically, in the route type 2, there is the field which is like the sequence number, and when the sequence number is higher, everyone will automatically override this information. So basically, everyone will immediately know that right now this MAC address is not available behind the L1, but is behind L3. The last important part is basically integration of the L2 and L3 together. This slide is a little heavy. I tried to put the most of the information to the single slide to let you adjust later on when you will be looking at the slides, which I will post on the page. Here, in this case, imagine that you want to have like your default gateway to be connected directly on the leaf, right? So you are basically from the VM point of view, your default gateway is on the leaf 1, leaf 2, leaf 3, and leaf 4. How I will achieve something like this when I have one single segment, right? Imagine that right now I have one orange segment, and basically the default gateway needs to be on all the four devices. I will configure the Anycast BVI, which means I will configure the IP address inside the bridge domain, which will be everywhere same, and I will also configure everywhere the same MAC address for this interface. So it means when the VM will be forwarding the traffic, doesn't matter if the traffic will hit like the gateway on the L1, L2, L3, L4. It is all the time same. This looks very easy from the configuration point of view, but you need some mechanism how you will synchronize these informations, right? So first thing is that you need to know on the L1 and L2, you need to synchronize the ARP information or neighbor discovery information. So when we will look at the ARP particular, right? So imagine that the L1 will send the ARP request and to the VM sitting behind the compute 1 in this orange subnet. When the M1 will reply, you need to synchronize this information also on the L2. So basically, L2 also needs to have this ARP information because they both are active and both are needs to be ready for forwarding towards the access. What will happen here is that I will use the same route type 2, which I was using for the advertising the MAC address, but this time I will also add the host IP address of the VM. This IP part is not mandatory in the route type 2. It's optional. So basically, you will advertise the MAC address. You will also advertise the host IP address. And you also know from which ESI it's coming. So basically, same like before, the L2 was synchronizing the MAC address table and pointing to the same Ethernet interface. In this case, I'm synchronizing my ARP information, which is very important. When I will synchronize my ARP or ND for IPv6, I'm ready to forward any traffic which is coming from core to the access. On the other hand, the L3 and L4 will basically put this host IP address to the forwarding table, to the FIP, because they need to know from the L3 point of view that this particular host IP is available over L1 and L2 because you are doing the stretch of the subnet. So then, when you have something like this, like you are able to basically put your basically default gateway directly on the leaf. So you have something what we call distributed anycast gateway. You can do your routing and bridging decision directly on the leaf. So you are getting a completely optimal forwarding from the south to north and also from east to west. So in this example, when you have two subnets, and imagine that you will first you want to forward between the same subnet in the red subnet which you have on the leaf 1 and leaf 2, it's a basically bridging. So when there will be packet coming or frame coming on L1 and you want to set it to the destination, the MAC address which is setting behind the leaf 2, you will just do the bridging over the core as we described before. But now, because you also synchronized, or you also advertise this IP part of the subnet, so you also have this forwarding information in your FIP. So it means that when you will get the packet, which is basically right now you are reaching your default gateway, for example, on L1, and you want to send it to this host behind L3 and L4, you will do the routing, the normal routing which you are normally used to from the L3 VPN world. So basically, from the L3 point of view, it's a normal routing, normal IP packet over the MPLS core. So again, you are doing your routing and bridging decision directly on the leaf, so you are always getting the optimal forwarding. This is everything what I have today. So again, I'm trying to keep it super short. I'm trying to have it like really short for you with some of the technical informations. I always expect that if you will have more interest in the particular area, you can search for more of the information. You can also go on the e-vpn.io and look at some of the more documents which we have there, which are describing the more of the details. I will again post this presentation on this page, so you will be able to download it later on today and go over the details and basically really understand what and how the EVPN works in this mode. Okay, again, thank you for watching, and let's see which topic we will prepare the next time. Thank you.